Thank you.
All right, thank you. First of all, thank you for the invitation and the efforts in organizing. Want to give a shout out to Thales Rick Perch, who's organizing this at the international level, and the local organizing committee. This is Maria Rosa, Carol, Everett, and Jose, if I'm not, hopefully not forgetting anybody. Thank you very much for this. I'll try to be, I have to tell you one thing. This talk ends with a picture of Boris and Thales. So if I don't get there because of time, you just look at them, and it's going to be very similar to the last slide, okay? All right, what am I going to talk about? So it was difficult to select a topic that could be entertaining for everybody, for a wider audience, so I decided to go with this, which is nice. This is, I'm going to talk about quantum energy teleportation. Quantum energy teleportation is a protocol of relativistic quantum information that does something that we couldn't do without taking advantage of quantum information, and in particular when you apply to quantum fields, a fully relativistic one, that has been recently proven experimentally. So I'm going to talk about what quantum energy teleportation is, how it connects a little bit with thermodynamics, with quantum thermodynamics. We're going to talk about the basic example of it. We're going to talk about the experiment, or at least the ones that I've been part of, how the experiment that was done here at the IQC, that the first proof, experimental proof of quantum energy teleportation. And we're going to talk about the consequences in field theory and future avenues of research that we're pursuing related to that. All right. So by the way, this is written by, oh man, there's no pointer here, huh? Here, oh yeah, there we go, my bad. This actually was written by him. I asked him how to say quantum vacuum in Japanese, and he wrote it for me, which is nice. So that's why I have it there. Masahiro Hota, if you didn't recognize him, by the way. Professor Masahiro Hota from Tohoku University in Japan. All right, so basically this is the outline of the talk. Let's proceed because time is limited. Let's talk a little bit about thermodynamics. Now, passivity of thermal states. What's passivity? Passivity basically is the property, passivity, you want to call it unitary passivity, is that, well, no matter what operation I do in some system, imagine the system is in a thermal state, in a passive state in general, I do some unitary operation, there's no way that I'm going to be able to extract energy from the system. So the cost of the operation, if you compute on average the expectation of the Hamiltonian after the operation minus the expectation of the Hamiltonian before the operation, you're going to get that it's going to have a positive energy cost. Okay? There's no possibility of extracting energy from it. As you know from your thermodynamics, basic thermodynamics course, if you have a thermal background, there's no way to extract work from a thermal state. Agreed? All right. Now, of course, we know that there are ways to extract energy from a thermal state of some finite temperature, right? Typically, you can couple it to something that is in a thermal state of lower temperature, for example, right? So if you couple your system to something that has lower temperature, then there's going to be an energy flow from the hotter system to the colder one. Agreed? Heat flows are established from hot to cold. There's the second law of thermodynamics. So we know that it's possible to do it. And indeed, if you relax the unitarity and then you say, well, if I do a CP-TP map on the system, so in general, I could extract energy. However, something that I want to note is that the thermal flow, right, when energy flows from a hot system to a cold one, you need time evolution. So you see, time evolution is not local in the sense that it's not a local operation on one side. I'm doing a contact here, thermal contact. I touch the corner, and energy comes to me, but it's certainly through time evolution. That involves, you need time evolution and you need energy flows. Internally, if you want energy flows, you need to involve everything in the system that you're talking about. It's certainly not only the site that you're touching, right? So in particular, one question you can ask is, can you actually extract energy purely locally in the sense of, I want to touch B, and I don't want anybody else to participate in the operation. The operation I'm going to do is only a local channel on B without letting time evolution do anything. Okay? I want to do something very fast, let's say. So the idea is this. I have a hand here. That's Masahiro's hand, for example. And it's colder than the system. The system is at some temperature T, and the hand is a thermal state of some temperature T hand. Okay? And then we do this. Imagine this is the sun, for example, and we touch the sun. The question is, will the hand get burnt or not? Would you get burned if you touch the sun? Well, the answer is not in general, no. In fact, the hand could get cooler If you touch something, you know, well, no, if you touch something very hot, very fast, you don't necessarily get burnt. You need some time to establish thermal contact. In fact, the study of these properties, was talking about this property is called strong local passivity. Strong, as in not only unitaries, but any CPTP map. Local, it only involves one element of the system, one subsystem of the lattice that we're considering. And passive, meaning that no possibility of energy extraction. So these two papers here prove a sufficient condition for strong local passivity, which basically, if the ground state of the system, think of the system, contains max rank entanglement. Max rank entanglement means that it spans, you know, the Schmidt composition of the ground state spans the whole Hilbert space. Then there always exists a temperature T star strictly larger than 0, for which, for the temperature T below T star, it is not possible to extract work from the system. So a system whose ground state has max rank entanglement, there always have some range of temperatures for which it is strong local passive. You cannot, by touching very fast, you are not going to be able to extract energy. In fact, you're going to have to pay energy if you do it. Make sense? That was, I have to say, we did work on this as well. We found that's a sufficient condition. We found the sufficient and necessary conditions for this. And just a shout out, this is in this paper by these people. I like to say it to show the people. Álvaro Martín Alhambra, currently in Madrid, in Autónoma. Giorgio Stilaris, I actually don't know where he is now. Nayeli Rodriguez Billones, that's in California. And here we have Jun Sikora, who was at Perimeter at the time, a postdoc at PI. So if you want to check that, that is with some interesting examples, that's sufficient and necessary conditions for strong local passivity. Anyway, so the idea is that you can have a strong point contact interaction, something that lasts for very, very short times. And because the system, keep in mind, is T below T star, meaning that for T equals 0, if you have a T star different from 0, and any temperature below that, the state is strong local passive, that means that the vacuum is indeed strong local passive as well, the vacuum, the ground state, right? So yeah, it could happen that you can touch the sun, and you can become colder if you touch it very fast. Disclaimer, I haven't computed T star for the sun, right? So I don't know. It may be or maybe not. But what I mean, you can definitely touch something hot with something cold and not get burnt and actually lose energy by doing it. Okay, that's the core of the strong local passivity result. All right. Now, can you break strong local passivity? Well, it turns out that, of course, with local operations of any kind, you can't. That's the definition of strong local passive. But if I add CC, if I add classical communication to the mix, I am able to break strong local passivity. For example, I mean, I'm not gonna show you the calculations because of time, but for time, because in mind that you have a system of two this is the minimal QET. You have a system of two interacting qubits. You make a measurement on the first system. The measurement costs you some energy, EA. Then you send the information, you generate a bit of classical information that you send over to B. Then B does some unitary operation that depends on the outcome, and that can be made so that the energy cost of that operation is negative. And that is, of course, in time sufficiently fast so that energy doesn't travel from A to B. There's no traveling of energy from A to B through their coupling. It's just the fact that you unlocked the access to the, if you want, the local, let's call it vacuum energy density, and you can extract it by no means. Okay, that's an intuition idea. Let's just show you the intuition. The intuition idea is, well, if you randomly measure, think of a vacuum or a ground state of something, it's a quantum system. If I randomly measure, sometimes it's going to cost me energy. Sometimes I'm going to have to give energy because the thing is fluctuating. So sometimes I'm going to, in mind it's rotating like this, the fluctuations are moving, sometimes you push it in the right direction, sometimes you don't. The fluctuations can be positive or negative. However, if somebody measures something else that is entangled with your system, that's something else, by measuring the thing that's correlated like that, you're going to learn about the fluctuations, then you know exactly in what way to push to always extract energy from it. Suddenly those fluctuations are no longer considered like random fluctuations in both directions. You know how to take advantage of them to actually measure in the right direction and extract energy. It's a bit of intuition behind the protocol of quantum energy teleportation. The protocol of quantum teleportation goes like this. So we start from the system ground state, for example. It doesn't have to be a ground state. It just needs to be some state with some temperature below some threshold. Then Alice carries out a projective measurement on her qubit. The result is announced to Bob. Bob carries out a unitary operation that depends on the result, and Bob can extract energy. Don't have the time to show you the math. It's very simple math. I actually cover it in my PSI course in quantum information or relativistic quantum information. So if you want to go to PIRSA and see it, it's a very simple example to see the minimal model. All right. So that's quantum energy teleportation as its simplest, if you want. Now, let's see an application of quantum teleportation by introducing a new idea in quantum thermodynamics that's called algorithmic cooling. Algorithmic cooling is precisely this thing. You have a fridge with an H-bar somewhere, right? And the idea is this. Okay, I have the following problem. I want to cool down these qubits. Maybe this one in particular that is hot. And I have access to a thermal bath. And the thermal bath is colder than the system. Nice. But my problem is I actually want to cool down this qubit below the temperature of the thermal bath I have access to. So then it's a little bit, you know, it's a little bit different than the fridges that you used to, right? With the fridges that you used to, you can only cool to the cold source of the fridge. You cannot cool below that. But, you know, doing some quantum manipulations, you can actually cool below, the idea is you can cool below the temperature of the thermal bath. How? Well, you do something called entropy compression. This entropy compression is a non-local operation on these qubits. What this entropy compression does is, here, I don't know why. You start from these guys, and then I do a unitary operation involving all these guys. And the unitary operation, what it does, it puts all the entropy, or as much as possible of the entropy, on one side. That way I have something that is hot in here, and something that is colder in here. Then what I do afterwards, I replace this qubit, or I put this qubit in touch with the thermal bath. When I do it, that qubit becomes as cold as the thermal bath. Agreed? Then what do I do now? Well, I do another entropy compression, and I put all the entropy in here. I dump some of the entropy to the thermal bath, and by rearranging the entropy in the system, by doing non-local operations, I put as much as possible of the entropy here, in a way that this guy actually ends up being colder than the thermal bath. So using manipulations of quantum information, if you want, using the fact that you can apply a non-local unitary here, you can reshuffle the entropy of the system to put all of it in a partial state of the system that you reset with the thermal bath. That way you can cheat. The more of this you have, the more you can cheat it, and you can cool partially part of your system colder than the thermal bath that you're in contact with. There are several techniques of algorithmic cooling that were developed, but almost all of them are designed to apply to systems that don't interact. So you cool down the system. If the system actually in mind that I want to cool, in mind that these qubits that I had here were interacting with each other. So if they're interacting with each other, this becomes trickier. And the reason is that, well, I'm going to have to go through the whole animation. It becomes trickier because if they are interacting, if you cool down the whole system, you have a problem. The subsystems are going to be mixed because the ground state may be entangled, and in general, it's going to be entangled. So if you want to cool one of the qubits, and you say, okay, let's put everything to absolute zero. Well, no, you don't get a pure state anymore in the individual qubits because, you know, the ground state contains entanglement. So they're going to be mixed states, the individual ones. Then, okay, fine, we can break the entanglement through, you know, make it interact with that environment. Sure, but that implies actually including mixedness in your system. It's going to be bad for you. Okay, we can apply local operations on the subsystem. If the system is local passive, as most, by the way, those conditions are fulfilled. For example, in a lattice of qubits or harmonic oscillators with first neighbors interaction, T star is definitely much larger than 0, which is saying nothing. It's large, much larger than that small amount. It's not small. That's what I mean. So yeah, indeed, if you apply local operation of the system and the system is local passive, you're not going to be able to extract energy from just interacting with the system. So you're going to actually put more energy into it that goes against cooling it down. So interacting systems, cooling down interacting systems with the usual algorithmic cooling algorithms is not ideal. It's not optimal. They're not designed for that. So we had this idea of applying quantum energy teleportation to do algorithmic cooling, because quantum energy teleportation precisely uses the correlations to extract energy from a part of the system. So that worked out. I did that with Ray Laflamme, well, Nayeli, Achim Kempf, that he will give a talk at the end of this session, and Ray Laflamme. And yeah, this is a bit of a comparison. Let me just show you the comparison with a little bit of interaction. Now, of course, the more interaction here, you see that the more interaction you have, the higher the interaction K. This kappa here, which is what K says here, this kappa here is the strength of the interaction. This is an interaction between qubits, right? The stronger the interaction, the more you can purify using QET. the less you should use the usual algorithm and the more you should use QET. And in fact, you do a comparison here in a case with a coupling of 0.2, strong but not too strong. And you see that QET cooling, which is these two curves, destroys HVAC. If you apply the usual heat bath algorithmic cooling, the methods using QET are much better. So you can actually use this protocol for algorithmic cooling when the systems have interactions. Nice. So hopefully I convince you that quantum Energy teleportation is cool. Now, it's kind of interesting, right? Because what I'm telling you is this. Why is it called quantum Energy teleportation? People don't like this name. I have to give you this disclaimer. Some people don't like it, and people confuse it with quantum teleportation too, which is not the same at all. I'm telling you that you put some energy here in one system. You don't let the energy travel to B. But the energy that you put in here, you use it to measure. You measure something, and that costs you energy. Of course, if you're in the ground state, anything you do is going to cost you energy. So that costs you energy. The energy that you put in doesn't travel to B. Only the classical information of the outcome of the measurement travels to B. And armed with that information, I'm able to extract energy from the ground state locally. It still looks like the ground state locally. I'm not able to tell it's not the ground state locally, because whatever perturbation I made here by measuring has not propagated yet to where I am. Does that make sense? So something that looks like the vacuum. This is going to be important when we go QFT and cross spacetime. It's very important. Energy has not propagated from A to B. And yet B, looking like the local vacuum, like the local ground state, I still can extract energy from it. That's so incredible that the first paper that Masahiro sent about this was rejected, saying that it's crackpottery. It was not. But the idea sounds very similar to extracting zero-point energy. And that's why some alarms were triggered, let's say. The one way to actually see that this is the case, right, you just do an experiment and check if you can actually do that. And indeed, we did it. The experiment was done, again, there's a group of Ray Laflamme, there's Hemant, was a postdoc at the time with Ray Laflamme, was also a student of Ray. Nayeli, I didn't say, but Nayeli was a shared student between Ray, Achim, and I. One recommendation, if you ever become a professor at UW, don't ever do triple supervision. It's a bureaucratic nightmare because the system is prepared only for 2 supervisors. Anyway, so the experiment here was using a molecule they know well. In fact, you can tell that Ray has the molecule in his hand, well, rather a representation of the molecule in his hands. So this is the molecule, transcrotonic acid. Details are not that important. The details that we implemented is that, well, here you can identify 3 qubits. We have an ancillary qubit, A and B. And the idea is that we're going to do an operation on A, the equivalent to a quantum measurement. The measurement is coupling the ancilla. Then we're going to decouple the ancilla. The nice thing about this is that we have full control in nuclear magnetic resonance. They have full control. They can engineer pulses that couple and decouple everything with each other, which is great. A and B are never coupled. They couple. There's some coupling always, of course, through the structure of the molecule, but the coupling is much weaker than the coupling between A and the ancilla and B and the ancilla. So the idea is we make a measurement. Instead of doing a classical measurement like a projective measurement, we do a quantum measurement. We let the ancilla interact with A, right? Then that causes some energy. And then what we do now is, without letting energy propagate from A to the ancilla and B to the ancilla, just the information, we apply a unitary operation on B based on measurements on the ancilla. So this is a scheme of the diagram of the circuit. That's the minimal QET. In any case, the nice thing is that if you do the calculation, the theoretical prediction is this red line of the amount of energy that you can teleport doing that. The dashed line is a simulation where they actually take into account the inefficiencies of the experiment that they have modeled really well. And as you can see, the experiment kind of fits. I always ask them, but the error bars don't fit. They don't care. So it's not that important. I don't care either, because the important thing is that the real experimental value is different from 0. So you are extracting energy. And the nice thing is that you can actually check if this was teleported or if the energy actually propagated, because you can still say, oh, come on, you put some energy in A and propagate it to B, right? No. The total duration of the experiment is 30.6 milliseconds. This is is the sum of the pulse duration, the duration of the pulse that prepares the interaction, and the duration of the different unitaries. And the energy propagation time is based on the coupling strength of this molecule. The time that it takes from let's say, 10% of the energy of A to travel to B is 1 second. And the whole experiment was 3.6 milliseconds. So certainly there hasn't been enough time for energy to propagate from A to B, and that's why this was regarded as the first experimental proof of quantum energy teleportation. All right, how much time do I have? 5? Poof, let's run. Here's an idea that came out of quantum energy teleportation. Can we use quantum energy teleportation to prepare exotic states of gravity? So the idea is doing something. This is with Nick Funai, who's here, was a PhD student of mine, now in Australia, in Melbourne, a postdoc, doing something like that. That's what I want to do. So I don't know how familiar, but I'm going to assume that there's some familiarity here with general relativity, but in particular, Einstein equations. General relativity is not reasonable, really, if you think about it. Put aside that general relativity predicts its own demise, right? But not only that, general relativity can produce monsters. There are some solutions to Einstein equations that are not that reasonable, right? Solutions that contain, I don't know, closed time-like curves, wormholes. No, a lot of things that are not really that reasonable. Warp drives, that kind of stuff. Well, there's a series of assumptions about matter, the matter that sources gravity, that make your life much easier, or make the theory much nicer, in the sense that they forbid to different degrees the existence of these exotic solutions that have closed time, like time machines, or warp drives, or wormholes, these kinds of things. In particular, those are the energy conditions. The energy conditions, I mean, you have modes by the weak energy condition. There's no such thing as negative energy density. Strong energy condition, gravity is only attractive, dominant. Energy must not flow faster than light. Null energy condition, positive null flow or stress energy density. Well, this is a difficult one to get intuition on for the time we have. But they seem reasonable enough. But keep in mind, general relativity does not guarantee any of this. These are things that you can impose on top of general relativity, because it so happens that the matter that people knew kind of satisfies that always. So people were okay with that, with imposing that. Now, of course, you violate, you get exotic solutions, we know that. But it turns out that, at least on average, quantum fields can violate the energy conditions. So the moment you do quantum field theory, the energy conditions no longer apply. They can violate all of them. I'm showing you an example of violating the weak energy condition, but they also violate the null one. That means that they violate every single one of them. You can prepare states of matter that in principle violate those conditions, so it's not guaranteed that if you use QFT, you're not going to be able to prepare, at least on average, those exotic spacetimes. So what's the back reaction of spacetime to that? That's not known. So let's turn to quantum energy teleportation. Masahiro did something. When Masahiro first proposed quantum energy teleportation, he did it in the context of QFT. Masahiro did the following: 1 + 1 dimensional quantum field, and I'm going to couple Alice only to left-moving modes of the field. You can do that in 1 + 1D massless field, the modes they couple, the right and left movers, so he did that. Couple Alice to left movers, and then what happens is that Alice makes a measurement by coupling something to the field. This is the energy density, okay? So after doing the measurement, the energy is dumped in here. Then the energy propagates to the left, because again, Alice is not coupled to right movers. Alice is coupled to left movers only, right? So the energy never reaches Bob, but then Bob gets some information of the outcome of Alice's measurements, and then Bob can actually do energy extraction, here, without having received any energy from Alice. Now here we're not going to focus on the energy extraction, we're going to focus on the fact that the energy density is that of the vacuum initially. The energy density, except for 0-point terms that are renormalized away, compatible with flat spacetime, right? It's 0. The energy density is 0 at Bob's position. So if Bob can extract energy from the position where Bob is, the energy density around Bob will be negative. Here's violation of the weak energy condition. So the idea is, and I'm not going to go through the details, what we did, instead of that, we did the case where, of course, you don't couple only to left movers, and you don't do it in 1 + 1D. If you don't, of course, both the information travel at the same speed as the perturbation. So if you really want to create negative energy density, you need to compensate for the positive energy density. I'm not going to bore you with the details. I'm going to tell you that we actually found a protocol based on quantum optics using atoms, like clouds of atoms, that couple to the field, and then you transmit the information from those atoms to another set of atoms where you actually can do it. In principle, at least in a sci-fi experiment, you can address these atoms with lasers at the positions they are. They are realistic probes. And the idea is, this is an example in 1 + 1D. You can tell that the calculation in the end gives you some terms that can be negative. In particular, this term, the expectation value of the original state on sigma y can be negative or positive. So these terms are the energy that it costs you to couple to the field, but then there's some contribution to the stress energy density that can be of negative sign, and at some points this can overcome these terms. So I can show you, this is the one, we did it in 3+1, not going to show you, but this is the 1+1 dimensional example. So Alice couples to the field. When Alice couples to the field, this is the energy density distribution on the field. After it couples, then it evolves in time, and then at some point, it gets to the position where Bob is. Now Bob is going to couple to the field. After Bob couples to the field, notice the rescaling of the axis, right? Bob puts more energy into the field by coupling, right? But when you let things propagate away after Bob does the thing, you get this distribution of negative energy surrounded by positive energy, something like this. Now, of course, I'm not going to talk, there's some complication of doing it in 3+1D, not going to get into them. But the idea is that you can actually overcome it. You can actually approximate a cloud with some density of atoms of detectors by a model that is simpler, would allow us to do the math, and then some equivalence between LOCC and LOQC for the communication of the information. But the point being that these kind of protocols, when used, quantum energy teleportation, when optimized to generate optimal negative energy distributions, can violate the quantum interest conjecture and the quantum inequalities optimally, the same way that something like the extreme dynamical Casimir effect. And you can scale it, the total amount of negative energy is unbounded. What you need to do is increase the density of your detectors and increase the strength of the coupling. If you rescale the strength of the coupling and the density of the detectors, you can get arbitrarily negative energy densities with this. Of course, the pay-you price is that they're in a tighter region of spacetime. Now, the one thing that I want to tell you to end, this is the last slide. As I promised, we end up with pictures of Boris and Rick and Eric's netter here. What we're trying to do now, so we prove already that you can use quantum energy teleportation to generate the stretched energy densities associated with a warp drive, for example, at least the ones that you need in order to build a warp drive. You can, with a protocol that you can do in a lab, or a protocol that's experimentally tested. You can, in principle, use it to generate exotic distributions of matter. Now, the problem with this is that, well, I mean, you've done the whole protocol assuming a static, flat space-time scenario. If you really want to tell me that you can build a warp drive with this, not, by the way, I never said that, but if you really want to tell me that this is going to generate exotic solutions to Einstein equations, what you need to do it is turn on gravity while you do it and see how the metric reacts when you try to do this. You're trying to bother the metric so much, annoy the metric so much. Oh, are you going to give me that matter, very exotic matter, that general relativity doesn't really want to deal with because it's going to look very bad in the eyes of physicists? But then we force it using quantum energy teleportation. How is gravity going to react? Is gravity going to allow you to do it, or is it going to dissipate the whole thing and it's not going to work? What kind of metric backgrounds can you generate dynamically with these kinds of protocols? So this is a question that we're in the first steps, because it's not very non-trivial to do, as you can imagine, with Thales and Eric Snetter, who's the person, one of the most important people who developed what is called the Einstein Toolkit, a set of tools to work with numerical relativity. And then Boris, who's the local expert in numerical calculus. That is the person that when we discuss the physics and we say, oh man, but that's going to be so tough. And I say, well, that's Boris' problem. That's the kind of thing. So we hope to actually give you a very nice movie next time where we see the metric change as we try to force general relativity to produce exotic spacetime with exotic matter generated through quantum energy teleportation. And thank you for the patience. That's it.